Okay, there you guys are. So I apologize if you look at the Zoom meeting's stats, I know that the times are wrong there. But of course we're meeting at our class meeting time and I'm grateful that everybody got in. Today we've got a few things to do. There's still a little bit more material relevant to your homework that we need to cover. So of course we're going to do that. And then I also just want to get some problem solving practice. But the first thing we need to talk about is this last little bit in that section on limits. So let me get my .camera firing and the screen share set up. All right, there we go. So the last section in the book that I wanted to, the last part of the section of the book that we're working in right now that I wanted to talk about with you guys is in here. So we've talked about limits and how you can get closer and closer along the graph, and that's how you sort out your limit by thinking about what the y values are approaching as x approaches some particular number. But what we haven't talked about are these infinite limits. So I want to start talking a little bit about these guys today. It'll be the first time we get to use this lemnis gate, this infinity symbol, so that's fun. And then we'll just work a bunch of problems from the graph. So today is going to be a fairly soft day. This is MAC2311.004. And today is the 28th. And what we're going to talk about finish section 2.2, which is on infinite limits. Let's see. So, did you have a question you wanted to ask? There's a little bit of noise in the background there, so if you wanted to ask a question, go ahead. But otherwise, I'm going to go ahead and mute you. Were you looking to ask a question? No. Okay. Cool. All right. So yeah, this is all we're doing today. We're going to finish up section 2.2, which is talking about that last little bit there on infinite limits, and then we'll work some homework problems. A reminder that your first homework one is due Monday at the start of class. Of course, if you haven't gotten into WebAssign yet, you really do need to get in there and get that done. Remember, you don't need your access code to get in there and get started. Even if you don't have your access code for WebAssign yet, you can still go in using the temporary or trial access. Just register using the class key and you'll be good to go. If you do use the trial access, remember to buy and input your access code before the trial runs out, which is at the 2-week mark. So if you are using the trial access, that will expire on the 7th of next month. Okay, so infinite limits are what you think they are. They're limits that turn out to not have a finite value. So I'll say consider the graph y equals 1 over x. Hopefully we all remember what this looks like. The shape has a special name. It's actually called a hyperbola. And he has some asymptotes. So if I asked you to draw a picture of the graph y equals 1 over x, this would be fine. We should probably label a point or two. I know that the point 1, 1 is on there. I know that the point 2, 1/2 is on there. And maybe over here I'll label -1, -1, which is on there. what we want to do is, as best we can, make sense of this whole divide by zero thing. So calculus, in essence, is struggling with the concept of infinity quite a lot, like either infinitely small or infinitely large, which means we want to kind of understand what's happening on this graph as we walk closer and closer and closer to zero. So if we imagine trying to send x to 0 from the right, that means we want to ask, as I let x get closer and closer and closer to 0 from the right-hand side, what are the y values approaching? We can make a table. We can use a table. So I'm going to put in some x values here and some y values here. So maybe I'll look at x equals 2, x equals 1, x equals 0.1, 0.01, 0.001. If x is 2, then 1 over x, y is 1/2, we know that. If x is 1, then 1 over x is just 1. But what happens as I start getting like closer and closer and closer to 0? Well, if x is 0.1, 0.1 is 1/10. So the reciprocal, 1 divided by 0.1, that's 10. If you plug in x equals 0.01, you'll get out 1 divided by 0.01, that's 100. And if you plug in 0.001 for x, you'll get out 1,000. So it appears as x gets closer and closer to 0, which is what these x values are doing, right? 2 is kind of close to 0. 1, that's closer. 0.1, that's getting really close to 0. 0.01, that's only off by 1 decimal from, by 1/100th from 0. And so these x values, they are getting closer and closer to 0. Do we notice a pattern in the y values? As x gets closer and closer to 0, 1 over x is getting really big. And what's more is it's not just that it's growing, getting bigger and bigger, it's growing without bound. It's unbounded, meaning that you pick your favorite y value. I can find an x value so that the point on this graph is above whatever y value you choose. If you tried to kind of zoom in on what's going on there at that vertical asymptote, as we bring this point further and further to the left, it's going up higher and higher. And no matter where you tried to chop, say you said, okay, well, right here, maybe the limit as x approaches 0 from the left of 1 over x isn't infinite. Maybe it should be some finite number. You can take a guess at what that finite number might be. But if I bring x a little bit further to the left, we'll jump over that. So the limit as x approaches 0 from the right of 1 over x, we would say that this is plus infinity.
Can you say just infinity, or do you have to say positive?
I'm making the plus there just to emphasize that there is also a thing called negative infinity. But no, you could just write infinity. Just like with other symbols or variables, if there isn't a sign out front, we assume positivity. On the other hand, if we approach 0 from the right, if I send x closer and closer to 0 from the right-hand side, you can see we're doing the same sort of thing.
Left.
Sorry, here, let me move this up a little further. So he said the limit as x approaches 0 from the right-hand side here is plus infinity. If we were to try and come in from the left, these y values are blowing up, but they're blowing up in the negative direction. So, oh, I wrote right, didn't I? Yeah, sorry. So on the other hand, if we approach 0 from the left, yeah, if I try to sneak in this way, we see the same thing. We could make that table again, and the table would be identical, just all the y values would be negative. So because we are diving off to negative infinity, we say that this limit is negative infinity. And this is the sense in which people say 1 over 0 is infinity, right? Because if you were to just plug 0 in here, well, it's not careful, it's not rigorous, at least not in this setting, because 1 over 0 isn't technically a number, infinity isn't technically a number. But as x gets closer and closer to 0, 1 over x does get bigger and bigger and bigger, and it grows without bound. So we would say that that's infinity. And as we approach from the left, this will be getting larger and larger and larger, but it will be negative. So we'll call that negative infinity.
I mean, adding on to when you said like 1 over 0, if you were trying to do like long division, like using 0 as your denominator, you'd see that you have to multiply by like there's no number huge enough to give you like an actual number, because you could multiply by 0 if you do long division.
Yeah, that's a fine way to think of it too. If you write 1 as 1.00000 and you try to long divide, you'll find that there is nothing large enough to multiply that by. Yeah, no finite number. So there is some arithmetic with infinities that we should be careful of. So algebra and arithmetic with this symbol. So that symbol is called a lemniscate. It's like a sideways 8, and we use it just in place of really, really, really big number, like unimaginably big number that is bigger than any other number. If you add infinity to infinity, think really huge number plus really huge number, the result is a really huge number. And you can imagine inducting on this, so adding 2, 3, 4, 5, 6, adding n or even x copies of infinity. If n is positive, then n times infinity, that's also infinity. Infinity raised to the infinity. That's a really big number raised to a really big number. We expect that to also be infinity. So these sort of operations are okay, and we can make sense of them. But there are some that we need to watch out for. Some of your arithmetic rules break down when you start playing with infinity. I'm going to put this first one over here next to this because it's kind of similar looking. Infinity minus infinity. This is not necessarily 0. It's not necessarily infinity. And it's not necessarily any particular real number either. This is called an indeterminate form. Similarly, 1 to the infinity, this is indeterminate. And there's kind of two other places you can get in trouble here, and that's infinity divided by infinity and 0 divided by 0. These are also both indeterminate. Because infinity is not actually a number, we can't do all the algebra and arithmetic with it the way we can do with regular numbers. Even if you invent this symbol and you treat it like it's a number and you work with it the same way you work with a variable that represents a real number like x, you can still put together expressions which turn out to not necessarily make sense. This is the most obvious one, but we will encounter these down the line also. So let's get some practice. I'll leave that up here for just a second. Maybe, let's see. Let's think about f of x as the function 1 over x minus 2 squared. Find the limit as x goes to 2 from the left of f of x, and the limit as x goes to 2 from the right of f of x. So to do this, we would like to have a graph. I can see that if I plug 2 in for x, then this will look like 1 over 0 squared. That's 1 over 0. And so that might be infinity. It might be negative infinity also. So we need to be a little bit careful. The graph of 1 over x minus 2 all squared, hopefully we remember from our pre-calculus classes how to draw this. We'll have a vertical asymptote where the bottom is 0, that's at 2. And he's a shifted form of 1 over x squared. So he looks like this. Over there, and like this, over here. So you can see that if we were approaching from the left, if I was a little guy walking along this graph and I want to get my x coordinate closer and closer and closer to 2, my height, I'm going to break out through the roof. I'm going to break out through the top of the computer screen. This guy is going all the way up to plus infinity. And similarly, if my little dude's got a buddy on this side, if he starts walking closer and closer to 2 from the right, we're also going to plus infinity. So here, we could say that the overall limit as x goes to 2, without the one-sided stuff of 1 over x minus 2 all squared, we could say that that overall limit is plus infinity. Whereas with the previous example, 1 over x, as we approach 0 from the right, we went to plus infinity. As we approach 0 from the left, on the other guy, we approach negative infinity. So the overall limit there would not have existed. But as long as you're going to plus infinity on both sides or minus infinity on both sides, then we can be comfortable talking about this. Questions about this example? Anything feel weird or worrisome here? It's not too bad, right? It's not too bad. As long as you have the graph, it's not too bad. So one of the big skills in this class is definitely being able to sketch quick graphs like that to help us with these sort of problems.
I don't know if this is like the similar, it looks like the similar problem that was on the homework on number 16. It says determine the infinite limit.
Let's take a look at that. Yeah, so the other thing I wanted to do today was just work some homework problems with you guys. I think at least now we've got enough of a feel to go take a look at that. So you said number 16? Yeah, this guy. And this is also a good one. So let's do both 16 and 17. Number 16 asks, so I'll write this down and then switch back. Find the infinite limit lim x to 1 of 2 minus x over x minus 1 squared. So really what we would like is a graph. There are some things that we can kind of assume. Like in the previous problem, here the factor downstairs that's going to 0 is a multiplicity 2 factor, right? That factor is being squared. And that will have an effect on the shape of the graph near that vertical asymptote. If we were in pre-calc, I would say, let's sketch this graph and use that multiplicity information. I might first want to rewrite this as negative x plus 2 over x minus 1 squared, because that's sort of your standard form where the powers of the polynomial decrease as you go down. So the top and bottom here are both polynomials. This is a rational function. You know, we can find things like the x and y intercepts. The y-intercept comes from plugging x equals 0. So that will be 0 plus 2 over negative 1 squared. It's 2. X-intercepts, set the top equal to 0. We set the whole function equal to 0, but the whole thing will be 0 when the top is 0. That'll happen when x is equal to 2. So there's a neat symmetry there. That's 2 comma 0. And find the vertical asymptotes. There's just one of them. It's the line x equals 1 because that's what makes the bottom 0. Find the horizontal asymptotes. That comes from comparing the degree of the top to the degree of the bottom. The degree of the bottom is 2, which is larger than the degree of the top, so that HA will be y equals 0. And with this information, I could try to draw a nice picture. I know that I go through 0, comma 2. I know I go through 2, comma 0. Make this nice and big. I know that my HA is the horizontal line y equals 0. I know I've got a VA here. And that's about all I know, right? So imagine plugging in something between 0 and 1. You plug in something like 1/2. Well, then the top would be like 2 minus 1/2. That's definitely positive. And the bottom would be 1/2 squared. That's also definitely positive. So we know that we're approaching this asymptote like this. It couldn't be negative because if the function was negative anywhere in this region, it would approach down here because it would have to stay negative in that region. But because it's positive in this region, it has to stay positive in this region. So we're going to approach our horizontal asymptote from above like this. And then the way we teach this in pre-calc is that because this VA came from this even multiplicity factor, we don't change sign. If we start positive, we stay positive. So if we leave going up, we return. coming up. So we're going to have to do something on this side like this. But what's interesting is that we come down, we poke through here, but then we also have to come up to this horizontal asymptote. So we have to do something kind of interesting like that. Now, a little later in the course, I'll teach you how to find this point, this min, this little inflection point where the curvature changed, all that stuff. But for us right now, we're just focused on the behavior here. As we walk along this graph towards one from the left or from the right, in both cases, I'm going to plus infinity. So from the graph, we see, or we know, that the limit as x approaches 1, 2 minus x over x minus 1 quantity squared. And this is the overall limit now. I'm not writing the one-sided limit because we just talked our way through the one-sided limits. Those are both plus infinity, so the overall limit does exist, and it's plus infinity. If we went up on one side and down on the other side, then this limit would not exist, because positive infinity and negative infinity are not the same thing. But this would be a nice solution to this problem, where you sketch the graph, and then from your graph, you can determine what's going on with the function.
Gotcha, thank you.
Yeah, of course, of course. Now, I know that everybody at home has, I mean, you're on computers, and computers, there's lots of ways to get graphs. What I want to encourage you is to spend some time drawing the graphs. Yes, we could put this into Desmos. Yes, Desmos would give me a picture that probably looks even better than this. But I wouldn't have the same experience. I wouldn't be getting the same sort of practice that I would from drawing the graphs by hand. If you take the time to draw them by hand, even if you use Desmos to help you, if you get stuck or whatever, that's okay. Just try to notice patterns. Spend enough time staring at the shit so that you start to notice patterns. Like if this number is even, then these will point the same way. If this number is odd, these will point opposite ways, one up and one down. Start trying to find the connections between the shape of the algebra and the shape of the graph. And that'll go a long way for us a little later in the course. We said we're going to look at number 17 while we're here. So before I leave this guy to go to number 17, are there any other questions or comments? Everybody feels good? Okay. So, number 17 again, I'll do my best to duplicate the artwork here, although my art skills are limited. They want us to play around with this function. So this is homework 1, number 17. We're going, looks like negative 6 to 6-ish. Okay, so this is negative 3, 0, 2, 3, 4, 5. And it looks like something is going on here at negative 3. Looks like we've got a vertical asymptote there. Looks like something is going on at 2. And something similar at 5. So my curve then, this over here, goes through the origin, it's going up here, it's going down here, and up at both sides. Okay. How did we return from 2's? It's not. So this is a neat problem. The function you're given looks like this, and they ask you to find some limits. They call this R of x. They want the equations of the asymptotes, the vertical, just vertical? Yeah, just vertical. Okay. So this is the graph. Y equals R of x. The horizontal axis here is the x-axis. They ask us for one-sided limits or for overall limits. Just see there's a question there in the chat. Yeah, Sophia asked a good question. Why isn't infinity over infinity necessarily 1? I will give you a couple of examples there. I think that's a really good question. So they want limit at 2.
Some infinities are bigger than others, so.
Right.
Kinda...
That's one way to think of it. The cardinality stuff, different sized infinities, it is an interesting problem. And there is a way to relate that to what we're getting at. But I think for most people from the calculus perspective, easiest way to think of it is in terms of how fast the function is growing to infinity. So give me just 1 second. We'll talk about this and then we'll do a little bit of that. And then I want 3 from the left. And then as x goes to 3 from the right. All right. So for the first piece here, we want to know the limit as x approaches 2. So I imagine I'm walking along this graph somewhere here, and I'm getting closer and closer to x equals 2, right? Because x equals 2 is right here. As I go closer and closer to 2 from the left, I'm going down to negative infinity. And if I get closer and closer to 2 from the right, I'm also going down to negative infinity. So this one does exist, and he is negative infinity. Similarly, as we approach 5 from the left or from the right, as my x value gets closer and closer to 5, I'm blowing up to plus infinity on both sides. So this would be plus infinity. If I try to sneak up on 3 from the left, that means I'm over here. I'm approaching 3 from the left. I'll be coming along this graph, and I'm diving down to negative infinity. But as I approach 3 from the right, I'm going up to plus infinity. So from these two, we could deduce that the limit as x approaches 3 of R of x, the overall limit, this does not exist. Because the left and right limits are not equal. They asked us to write down the equations of the vertical asymptotes. Well, here's one of them. This VA is the line x equals negative 3. This VA is the line x equals 2. And this VA is the line x equals 5. Remember, equations of vertical lines are always x equals a constant. Okay. Any questions on this guy? A fun problem, and a problem that you can give at the pre-calculus level, would be to come up with a function that actually has a graph that looks like this. You know that vertical asymptotes come from factors of the denominator. You know that x-intercepts come from factors of the numerator. So we could construct a possible function. This is not a part of the problem. I'm just going a little bit deeper here. But one possible function with this behavior the VA at -3 has to come from a factor of x plus 3 downstairs, because that will make the bottom 0 when x is -3. And since we're going down on one side and up on the other, the multiplicity has to be odd. So x plus 3 to the 1, or x plus 3 to the 3, all of those would be factors that could contribute behavior looking like this. The x-intercept at 0 has to come from a factor of x upstairs, or x minus 0. The VA here at x equals 2 comes from a factor of x minus 2 downstairs. But since he's going down on both sides, since he doesn't change sign, he's negative here and he's negative here, it has to be an even multiplicity factor. So this could be x minus 2 squared, or x minus 2 to the 4, anything like that. And then we have a similar issue here at 5. This has to be coming from a factor of x minus 5 downstairs. But because we're going up on both sides, because we don't change sign, this has to be something like x minus 5 squared. Just for shits and giggles, let's throw that into Desmos. I don't have any guarantee that it's going to look exactly like our graph, but it should have those same features.
I have a question.
Yeah.
Can you repeat what you said about the when it becomes like a squared?
Yeah, so the trick to figuring out, think about 1 over x and 1 over x squared. 1 over x has a vertical asymptote at 0 because the bottom is 0 at 0, and it's an odd multiplicity. So you go from negative to positive. 1 over x squared, on the other hand, come back here. 1 over x squared, on the other hand, goes up on both sides. So this thing where you're the same sign on both sides of the vertical asymptote, either up on both or down on both, that's coming from the fact that the factor of the denominator that's giving you that feature is an even multiplicity factor. 1 over x cubed, 1 over x to the 5, they all kind of look like this. 1 over x squared, 1 over x to the 4, 1 over x to the 6, they all kind of look like this. So you can think of features like this or this as coming from translates or combinations of stuff like this, where you're same signed, either positive on both sides of the VA or negative on both sides of the VA. And you can think of things like this, where you're negative on one side and positive on the other, as coming from translates or combinations of functions like this. That's why the x plus 3 factor downstairs here that I cooked up, I gave an odd power to. But the other guys, like this, I gave an even power to. So it's to do with the multiplicity of the factor from which the feature comes. And it's something that's supposed to be taught in pre-calculus, but I think calc is not always covered the way it really should be, you know? So let's graph this. Let's graph r of x equals x divided by x plus 3 times x minus 2 squared times x minus 5 squared. So the scales here, I'm going to have to rescale my y-axis considerably. Is that better? Nah, it's still a mess. Why is that not listening? Oh, negative 100 to 100. It's still a little squished. That's okay. But you see here, we do have the same sort of features. Oh, maybe I'll go the other way. That's a little better, yeah. So you see here the behavior near negative 3. You're going up on one side and down on the other. You've got your x-intercept at 0. And then your behavior at 2. Here it's up on both sides and up on both sides. If I wanted to change that and make it go down on the one and up on the other, I would have to modify the algebra somehow. Honestly, I'm not sure a quick, easy way to do that. But it's nifty, right? To see the connection between the even or oddness of the multiplicity. Here's odd multiplicity, and here's even multiplicity. So even multiplicity, you'll do the same thing on both sides of the VA. Odd multiplicity, you'll do the opposite thing. Okay. So then the other thing that we wanted to address here is what's up with infinity over infinity? Why can't I just call that 1? Let's come back to that. Well, infinity is not a number. These always show up in limit situations. So let's try to think of a few ways we could get infinity over infinity. I'm going to need a limit. And let's do something like the limit as x goes to 0 of, let's go to 0 from the right. One function that I know will go to infinity as I go to 0 from the right is 1 over x. Another one is 1 over x squared, right? If we think about the graph of 1 over x, we know, oh, yep, yeah, he's going to go to infinity as x goes to 0 from the right. And 1 over x squared, he's also going to go to infinity as x goes to 0 from the right. But if I do a little bit of algebra here, I can just clean up the function inside. I'm not changing anything. Still going to 0 from the right. And what I'm going to write down here is I'll leave my 1 over x alone. But then I'll multiply by the reciprocal of 1 over x squared. That's how you divide two fractions, right? You leave the top alone, you multiply by the reciprocal of the bottom. That's x squared over 1. So this is the same. It's literally identical to x squared over x. But you can cancel an x. So you'll see here that infinity over infinity in this case is 0. Because you know, what does this graph do? Y equals x. Well, that's the line through the origin, slope 1. He has a little hole here, but the limit is 0. He has a hole because we're canceling. We can cancel this into this as long as x is not exactly equal to 0. But here, this particular flavor of infinity over infinity turned out to be 0. Or we could switch the roles. Another way to write infinity over infinity is the limit as x goes to 0 plus of 1 over x squared divided by 1 over x. Here, the top here is definitely going to infinity as x goes to 0, and so is the bottom. So this is infinity over infinity. But if you do the same sort of thing, you clean it up algebraically, this will be x over x squared, which is 1 over x. And this one we know is infinity. So here's two different infinity over infinities. On the one hand, infinity over infinity can come out to 0. On the other hand, infinity over infinity could come out to infinity. And in fact, it gets worse. When we talk about limits at infinity, like where you send x to infinity, instead of sending x to 0, you send x to infinity here, I'll be able to show you other examples where infinity over infinity could be any finite number you want. You could even get that here, 1 over x divided by 1 over x. That would look like infinity over infinity as x goes to 0. But there, the 1 over x's would cancel perfectly and you would get 1. So we could say Certainly here, the top is going to infinity and the bottom is going to infinity. But the numerator and denominator cancel exactly. This is the limit as x goes to 0 plus of the function 1, which is 1. So infinity over infinity could come out to 1, could come out to infinity, and it could come out to 0. It all depends on where it's coming from. This is why infinity is not a number. It doesn't satisfy the algebraic restrictions which numbers must satisfy. So like every non-zero number has to have a unique reciprocal. Infinity doesn't have a unique reciprocal. Every real number has to have a unique additive inverse, a negative, right? And infinity, although there is a negative infinity, they don't always add up to 0 for similar sort of silly things like this. So while infinity is a useful idea, it's definitely not a real number. It's not a complex number either. There are number systems that include infinity called the extended reals. And some people, especially in measure theory and statistics, care a lot about those. But because it doesn't satisfy the algebra properties we would like it to, infinity is not a number. It's not a real number. Okay. So the basic idea is that if, as you get closer and closer and closer to A, the y values along your graph get closer and closer and closer to infinity, then the function has a limit that we call infinity. There's a bunch of different ways you can say this. These we've already covered, the same thing. There's just one or two more examples that I would like to play with. I guess we should define, yeah, you know what a vertical asymptote is. But we can take all those things that you learned in pre-calc and translate them into the language of calculus. So definition, we say a function f of x has vertical asymptote x equals a, provided any of the following are true. The limit as x goes to a from the left of f of x is infinity or negative infinity. The limit as x goes to a from the right of f of x is infinity or negative infinity. And that's the idea. So if any of the one-sided limits for your function at that number are infinity or minus infinity, then we say that f has a vertical asymptote at a. And the vertical asymptote is the line x equals a. So let's look at any possible limits to 0 of f of x equals the natural log of x. The graph of the natural log is one of these things that, again, like so much in pre-calc, I can't be certain you got a good treatment of. So let me go ahead and remind you how he looks. The natural log of 1 is 0. So we know we go through 1 comma 0. The natural log of e, which is about 2.7, that's 1. And the natural log of 1 over e, or e to the negative first power, that's negative 1. So here's what the graph of ln x looks like. This should just be diving straight down there. Sorry, my penmanship is quite poor. But he continues down like this. All right. So this is y equals ln x. The domain of the function is just positive real numbers. So if I asked you to take the limit as x approaches 0 from the left of ln x, what would we say there? There's nothing over here to work with, right? Because no negative numbers are included in the domain. So this guy does not exist. Because the domain only includes positive numbers. I can't try to sneak up on 0 from the left and stay along this graph because there is no part of this graph to the left of 0. On the other hand, the limit as x goes to 0 from the right of the natural log of x, this is defined. What is this?
Negative infinity.
Good, yeah, negative infinity, because we're diving all the way down off the page here as you get closer and closer to 0. So every now and then you'll hear people say kind of tongue-in-cheek that the log of 0 is negative infinity. It's not rigorous, it's not entirely correct. It's like saying 1 over 0 is infinity. But the statement which is correct is that the limit as x approaches 0 from the right of the natural log of x, that is negative infinity. There is a related function that's kind of cool to look at, and we'll be working with that function towards the end of this class when we start talking about integration. Has anybody ever seen the graph of the natural log of the absolute value of x? This is pretty cool. So you take the regular graph of ln x, which is just this stuff, and you make it symmetric, about 0. So based on this graph, could you tell me what is the limit as x approaches 0 from the left of ln absolute value x?
Negative infinity.
Yeah, now we've got that symmetry, so we can say both of the one-sided limits are negative infinity. Therefore, here the overall limit does exist. And is negative infinity. So I think that's about all we really want to say about these things. It's the natural log. We can look at some. We should, yeah, let's do that really quick. But then I'm happy to spend the rest of the class doing anything else that you guys would like to do if there are other homework problems you want to look at. So let's do one more example here, and let's have it involve some trigonometry. Let's find all the vertical asymptotes for the secant function. So we'll want to look at a graph of secant at some point here, or draw a graph of secant. It may be wise to recall that secant is the reciprocal of cosine. So secant is going to run into problems when cosine is 0. And that will help us find our vertical asymptotes. But we remember from our trigonometry classes that the graph of secant looks like this. Kind of this bowl shape. It's not a parabola, but it's kind of similar to a parabola. And then you've got some VAs. And then you've got another copy of that sort of thing, only this time it's facing down. And then you run into another VA. And then he comes back up. And it continues like this forever and ever, amen. It's a periodic function. These guys are at height 1. This guy is at height -1. And of course, there's another VA over here. And that same pattern. So the graphs of your 6 basic trig functions, we do need to know these. So it's y equals secant x. And you see, as we approach this number from the left, we go up to infinity. As we approach this number from the right, we go down to -infinity. So this guy is definitely a vertical asymptote. Does anybody remember the x value here? Try to think of it like this. Think of it as 1 over cosine. That first place where this function blows up to infinity is going to be the first place where this guy goes to 0. What's the smallest positive number so that the cosine of that number is 0?
Okay, yes, one typed already.
Oh, I'm sorry, I don't see the chat here. Let me move this. Yeah, good, pi over 2. Harris got it. And because cosine is an even function, you know that this must be -pi over 2. This right here is pi. This is 3 pi over 2. This right here is 2 pi, and this is 5 pi over 2. This guy right here is -3 pi over 2. So you can find these VAs by thinking of this guy, by thinking of secant as 1 over cosine, and then just figuring out where cosine is equal to 0, because you know in the limit, as cos goes towards 0, secant will be going either towards positive or negative infinity. Some people I've seen draw the graph of cosine in here on top of this. Kind of help them visualize what's going on. And you'll see that the places where cosine is 0, those are the places where the graph of the secant function blow up to infinity or -infinity. So what are all of these? Do we remember enough trigonometry to remember how to write down the set of all vertical asymptotes here? Let's see, one of them is x equals pi over 2. Another one is x equals 3 pi over 2. Another one is x equals 5 pi over 2. What do you think the next one would be? You see a pattern in these?
I mean, yeah, 7 pi over 2, it's probably just
Yeah.
gonna, like, you do in parentheses 2, 1 plus 1, and then pi all over 2, and then like n is just like, what do you call it?
Perfect. Yeah, that's
Natural number?
so these are odd multiples of pi over 2. 1, 3, 5, 7, 9.
Okay, I'm enough the real numbers. There you go.
No. You said it correctly. You said it correctly. So
Oh, no, I'm saying, but like, I was gonna write in like, 2n plus 1 times pi all divided by 2, and then n is an element of the real numbers.
Natural numbers or integers.
I
Really.
mean, natural, yeah.
So this is the formula that you're referring to, right? Where the 2n plus 1, that is the odd number up here. And so the set of all VAs would be all of these guys, all of these lines, where n is any integer. Because we want to get the negative ones also, we have to allow n to be negative. That will allow you to pick up the negative 3 pi over 2 and the negative pi over 2 there. If you restricted just to the natural numbers, that would only give you the positive ones. And if you let n be any real number, then you're talking about a much, much larger set. It includes all sorts of other things, because you could plug in pi for n.
Yep.
So
Right.
this is the collection of all.
That's my bad.
Cool. All right, well, really, that is all I had for you guys today. So with the remainder of our class time, I will leave it up to you. What would you like to look at? Are there some other problems in the homework that you guys would like to talk about? What else did we have? I didn't hit you too hard for this first week. Has anybody gotten number 15 yet? This is a good problem.
Yes.
We did some stuff like that, but maybe a little more practice graphing piecewise functions. Let's look at 15. How are we doing on time? We're good? Yeah, okay. So we've got sine of 7 theta over tangent of 2 theta, and we want to send theta to 0. What do we say? 4 and 2, 7 and 2. And this is homework 1, number 17. And they tell you to use a table. Did she go? She did. All right. So we want to make a table of values that'll help us figure out what the limit as theta goes to 0 is here. So our table should have thetas, and I'll call this thing f of theta. And I want to try plugging in numbers that are close to 0. It's not easy to plug into these guys by hand unless you're plugging rational multiples of pi, and even that's not easy. So we're going to use some sort of calculation tool. But let's do like 1, 1/2, 0.1 or 1/10, 0.01 or 1/100th, 0.001, maybe one more, 0.0001. I'll pull up a calculator tool here. Okay. So that's not quite.
I have a question. Is there a way we can like put it in the calculator? There's a way I found out like how to get the answer, but is there like a different way we can put it in the calculator to find it?
I mean, you could just use Desmos like he's gonna do.
Yeah, any sort of TI-83, 84 can do what I'm about to do here. There's actually a function on most graphing calculators to spew a table like this straight away. But what I'm going to show you guys later in the semester, I'm going to show you a way to do this limit with calculus. So I don't want you to get too attached to the idea of using a tool like a calculator right now.
I mean, what I did, I kind of know some calculus, and what I did is like sine of x is approximately equal to x and your x equals 0. Then I got 7x all over, what is it, 2x, and then cosine would just be 1. So it's just 7 over 2 at the end.
Arguments like that can be made, but you need to be able to justify them. So we'll get there. For now, I want you guys to play along with me. So we're going to make sure we're working in radian mode. f of 1, if I plug in 1 for theta, I get negative 0.3. The approximations that you talk about making there, Alex, are true and correct, but we need some justification for them. So we'll get there very soon. I'll ask you to be a little bit patient because we got to develop all the theory. F of 1/2, if I plug in 1/2 for theta, I get negative 0.225. I'm not rounding anywhere in particular here. Just trying to get a feel. That's the idea of this problem. So they just want you to play around and start to get a little bit of a feel for what limits are and how they behave. This guy is 3.18-ish. Then we get 3.49. Then 3.4999. Then 3.499999. We got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah, okay. So from this table, as theta gets closer and closer and closer to 0, it looks like this function is getting closer and closer and closer to 3.5. And it's true that 3.5 is 7/2. So there is a direct relationship between these numbers and the value of this limit. But that exact relationship we won't discover until after we've talked a little bit about derivatives.
Question in chat.
Yeah, I see it. No, absolutely not. No Desmos during the test. So the test questions are going to be designed without any big calculations, and any graphing will be graphing that you are expected to know. So like graphs of sine, cosine, secant, tangent. A problem like this would not show up on your test. Yeah. So the only calculators that you guys are allowed to use during the exam is the TI-32XS. But I would never give you something like this on the test. So the stuff I'm going to put on the test, I promise, will be gentle calculation-wise. As long as you've learned the skills and tools that we're talking about in class, you'll be just fine, I promise. Alrighty. So is there anything else in the homework that you guys would like to look at or talk about while we're here? I think we still have a few minutes left in class. Let's see, 13? Sure. So I did something similar to this the other day, but I think graphing piecewise functions, we all need lots of good practice at that. So I'll write it down. This is homework 1, number 13. Oh shit, did I leave those windows open? All right, that'll be okay. So here, f of x is 4 plus x if x is less than 2, or if x is less than -2. It is x squared if -2 is less than or equal to x is less than +2. And it behaves like 6 minus x if x is greater than or equal to +2. So here's my function. It is a piecewise function. And remember, the way we come up with these graphs is by graphing each of the pieces on their own. And then just taking the parts of each that we want. So 4 plus x looks like this. X squared, like this. And 6 minus x, it's like this. Each of these are functions we know well. And my function behaves like the first guy, but only for x's which are to the left of -2. So where is -2 in this picture? Well, -2 plus 4, that's +2. So it's like halfway through this. So I'm going to take only the part of this graph that satisfies the condition specified in my piecewise function, just this part. And then from my parabola in the middle, I'll take the stuff from -2 to 2. So just this stuff. And from 6 minus x, I'll just take the stuff to the right of +2. 6 minus +2 is 4, so 2 is somewhere right around here. So that's this piece. Now I imagine that I could cut and paste these all together, just the parts that I want. That will be my whole overall graph. So down here, I'll mark off -1, -2, 1 and 2. To the left of -2, I behave like this guy. And because we had a strictly less than here, there's actually going to be an open ball here. Because at -2, I'm using this rule, not this rule. So I'll start with that. So that's this part of this guy here. Then from -2 to 2, inclusive on the left, not inclusive on the right, I'll behave like x squared. So I'll be open on the left and closed on the right. And the y value there is 2, the same as the y value here. So this is actually going to fill this guy in. Oh no, sorry, the y value there is 4, never mind. Sorry, so shit, this should stay open. So I goofed there, I'm gonna redraw it. I should not have filled that in. The y value on x squared is 4 there. Open like that. Okay. And then at -2, x squared is way up here at 4. And we will be behaving like x squared. We'll take this piece, so like that. And then continuing symmetrically over to here. And on this side, it would be open. So this is -1, -2, 1, 2. And then my last piece was the 6 minus x piece. That's this guy. He will match up with the parabola because when x is 2 here, 6 minus 2 is 4. That's the same as the y value on x squared at 2. So this will fill in. And we have the -1 slope line. So this is a nice graph of f of x. And we get it just by cutting and stitching these pieces together. The closed-in ball here filled in what would have been an open ball. Or sorry, the closed ball here filled in what would have been an open ball there. So this is part of 4 plus x. This is part of x squared. And this is part of 6 minus x. And that's how she goes. All right. It did just start to pour here, and I think I left my car windows open, so it's convenient that this is time for class to end. I will go ahead and end our video here. And I will see you guys on our next class on Monday. Remember, you have homework due, so please try to get that homework done before class on Monday. If you don't get it done by Monday, it's not the end of the world. You can just submit an extension request in WebAssign, look around on the page, you'll see a link that says request an extension, but you really want to stay on top of the homework right now. You do not want to slip. So we want to be working on drawing lots of graphs, make sure you're doing it by hand, not just picking or using Desmos. And then have fun getting comfy with the limits and the limit notation. Pay attention to what you write. Write everything. Don't get lazy and leave off the limb or leave off the arrow. Practice writing everything nice and neat, really, really pretty, and it will help us as we go deeper into the course where things get tougher. Alrighty, I will see you guys either in office hours or in class on Monday. Take care.